Hello everyone. If you'd asked me a few years ago if I'd ever be designing and making my own modular software-defined radio platform, I would have thought you nuts. Sure, I've always thought radio was one of the most exciting kinds of electronics magic, and no matter how much I learn about it, it never really puts a dent in the sense of wonder and amazement I get from playing with radios and gaining the sixth sense of seeing the radio waves all around us. Last time, we left off with what I called the bare minimum of what an SDR is. Some way of mixing radio down to IQ baseband and getting it to somewhere you can do some signal processing on it. And of course, I had to do that with the help of a 50-year-old CPU, the 6502. If you need a quick start on what software-defined radio is at an electronics level, you might want to check out the first video of this series. Since my little 6502 platform, the 6501, doesn't have much of an ADC to digitize the incoming analog data, at the moment anyway, last time I chose to do what you'd do 25 years ago. Feed it to a beefier computer through the best ADC most people had, the sound card. In 2025, that just about makes it the worst bandwidth you can get out of an SDR on the market, since we're limited by the 44.1 kHz of the sound card. That's about 72 times less than the common RTL SDR can handle, and not even enough to decode FM radio. And I plan to do a lot better than the few megasamples per second of the RTL SDR, so we're going to need a better approach than just a sound card. We're not going to reach double-digit megasample rates today though, but I'd like to take a little detour before putting up a fight with the fancy SDRs. And that's because I've had these blue pill dev boards, yes, I know this one's black, but that's what they're called, in the back of my closet for a few years, and for a few dollars, they're remarkably powerful. Coming in cheaper than ESP32s, and with a set of features extremely suited for this project, I thought I'd give it a go. Since the STM32 F103 on the board has USB, DMA and dual ADCs, it's almost like it was made for a task like this. You see, it's not too uncommon with some sort of ADC and a USB interface on some of the mid-tier MCUs, but more common than not, the ADC only has multiple channels muxed to a single ADC. And since we need both I and Q sampled simultaneously, we actually need two independent ADCs linked together, and this low-cost chip just happens to check all those boxes. Of course, I didn't have great expectations for a cheap MCU, but I thought it was worth seeing just how much I could get out of it. It wasn't great at this point for a number of reasons, but I managed to get enough bandwidth out of it that I decided to make my own board with the help of this video's sponsor, JLC PCB. JLC PCB makes PCB fabrication and assembly easy, affordable, and reliable. The perfect combo for anyone who loves bringing electronics projects to life. I've been using JLC PCB long before they ever sponsored me, and they've always made the process effortless. Their website is simple to navigate, their pricing is super affordable, and their service is consistently dependable. Even when I've pushed the boundaries of what's possible, they've had my back every time. If you haven't tried them yet, you can get your first PCB for just $2 and claim $70 in coupons. Whether it's your first prototype or your 100th build, JLC PCB keeps it stress-free, budget-friendly, and rock-solid reliable. Thanks to them, I can focus on what I love, creating new projects and sharing the extra boards with you. I suspect the blue pill boards are usually just double-layer boards without a dedicated ground plane. But with the main feature of this board being the two ADC channels, I decided it was worth increasing the cost a bit to get good separation between the incoming signal and the noisy USB lines going out the other end. The main idea with this board is just to capture the I and Q channels through a passive LC low-pass filter for anti-aliasing. That is, limit the frequencies to what the analog to digital converters can handle, like we went over in the first video. I haven't used STM32s a lot in my designs for no particular reason, but they're really easy to get running with not much more than a crystal, a few caps, and a reset pull-up. I hope I didn't say that too fast though, as I haven't even checked the voltages yet, so that's probably a good first step before we throw some firmware on it. Looks like we have a 5.2 volts coming in through USB-C, and the onboard LDO is happily supplying 3.3 volts to the chip. Yay! I'm also a little bit curious if the oscillator is running from the factory, but probably not. Nope, nothing making 8 MHz and nothing making the slow crystal tick either. Programming STM32s is either done through an on-chip serial bootloader or serial wire debug, which is a common standard for programming ARM core MCUs instead of JTAG. Luckily, these ST-Link V2 dongles are super cheap and also come built in with even the cheapest of ST's development boards. I've put optional jumper pins on the board that you can use to start the serial bootloader to just use a normal UART or debug code from SRAM, but the cool thing about using the ST-Link is it only requires ground, a clock, and an I/O pin to program the built-in flash. So I'll just hang off some jumper wires, and with a little bit of luck, I can program it without even soldering in the programming header. And by the look of the onboard LED, programming was successful. If we check using the scope, we should see 8 MHz clock the internal PLL into 72 MHz. The 2C53T I'm using here I got from FNIRSI, still no idea if I'm saying that right, and even though it's just a 50 MHz scope, I've been super happy to have a multimeter, signal generator and scope in one package that's not too big to take traveling. I'll try to put links to most of the things you see in this video in the description if you're interested. I've designed the boards with the same spacing for the SMA connectors, so you can just use 2 adapters like this to connect them, or a pair of equal length cables. Since I've already programmed the 65 Ueno to control the PhaseLoom, I don't need that hooked up to USB as well as the new board, so if I solder on a header for the 5V output, we can use a single USB cable to power all the boards. Of course, I could just add the code to control the PhaseLoom over I2C from the new board, as well as acting ADC and USB bridge, but for now I'm happy using both. Besides, I will be going down a different road with a bunch more bandwidth anyway. More on that later. Let's see what this can do. Hooking it up to my 40-meter band antenna in the garage, I get a few AM stations, a bit of Morse code, and the usual clear squeal of FT8 coming through. But I also see a bit of aliasing, and the further away from center frequency we get, the worse image suppression gets. That's kind of to be expected, since we're not exactly using a high-end ADC, and any internal imbalance will cost mirror rejection. But something tells me we can improve the performance by increasing the gain on the PhaseLoom. You see, the low-pass anti-aliasing filter on the new board is pretty lossy, since I decided to scale it to use smaller inductors. So the signal coming into the ADC isn't even close to clipping. Even the most powerful signals had trouble making it up to the -30 dB mark, so we have plenty of room coming into the ADC. I've already removed the 50 ohm matching resistors on the op-amp output because they were acting like a low-pass filter, causing a low-frequency bump on each side of the DC center spike. So if you have a PhaseLoom version 1, you might want to remove those too. We could put a low-noise amplifier before the PhaseLoom, and maybe we'll do that later, But since we also limit the bandwidth of the buffer op-amp slightly if we increase the gain, that might work out even better. To do that, it's a simple matter of increasing the feedback resistor size. But we have a problem. Since any imbalance in the signal coming out of the op-amp will cause an amplitude mismatch, it'll also cause IQ imbalance, which we'll see as even worse image rejection. To fix that, we need super precise resistors to set the op-amp gain. Unfortunately, I don't have any 0.01% 47K resistors that we can use to about double the gain from what we have. But luckily, we don't need all the resistors I have to be precisely the same value. We just need two that are close to each other. They don't even have to be very accurate, since we don't care if they're exactly 47,000 ohms, as long as they match each other very precisely. Which is why this little procedure I'm doing is called matching. I take a handful of resistors and I pick the two that are closest to each other in value. So even if they're sold as 1% resistors, we can find two that are within about 10 ohms of each other, making these resistors act like they're 0.02% resistors. With those in place, let's see if a stronger signal into the ADC makes things prettier. Back in the garage, things do look slightly improved, especially at the edges of the 200 kHz bandwidth.
Delta Mike 1, Japan Sierra 5915.
I'm receiving single sideband amateur radio pretty well.
Yankee Tango 9 X-ray. Yankee Tokyo 9 X-ray contest. CQ contest, Yankee Tango 9 X-ray contest. CQ contest, Yankee Tango 9 X-ray, Yankee Tango 9 X-ray contest.
And sure, it is nice to be able to cobble together a cheap shortwave receiver and receive a station at least 1,500 kilometers away, but I was still hoping for a flatter response, better image rejection ratio, and a cleaner spectrum. So I took it back to the lab, and when I measured completely clean IQ inputs to the ADC channels, I had to take a few days to think before I got some more progress. Since it wasn't a hardware issue up to the point the IQ signal reached the ADCs, the problem had to be somewhere after sampling or down from there. I haven't really talked much about the software side of this project. Trust me, that could be a very long video in itself. So I'm going to keep it short enough that anyone interested should be able to use the code available on GitHub. I've decided to call the project the PhaseLatch Mini because it's going to be a cheaper and way less powerful ADC than what I have planned later. And it simply consists of a platform.io firmware project and a few Python host scripts. If you follow the README instructions, it should only take a minute or two to get running. Since I haven't gone as far as to make a complete integrated driver for GNURadio or GQRX, my Python driver simply dumps whatever the ADCs receive into a FIFO buffer via USB that GQRX can read at the sample rate the firmware is set to using the file source. That means we can't control the frequency in software, but have to tell GQRX what the local oscillator is set for when the buttons on the PhaseLoom are pressed to change the frequency to a different channel. The current default configuration is 15 different channels in the 40-meter amateur radio band and a couple of channels in my local FM broadcast band. You probably want to change those in the firmware if you've tried out, and I'll demo my local ones in a bit. In the 6502 firmware for the PhaseLoom, I've given the SI5351 frequency selection a complete overhaul, since changing only the multisynth values meant either a bad frequency resolution or an incorrect phase offset, resulting in bad mirror rejection because the Q channel didn't have exactly 90 degrees offset. By only changing the PLL and allowing it to use a fractional divider, the multisynths will always have an integer divider, so we get a precise 90-degree offset no matter what the PLL is set to. You'll have to excuse the clipping of the audio from GQRX as I set the gain to 13 dB, which shows up as clipping in the audio. I hope you'll also excuse the noise, and maybe you can even help me translate some of what we hear and put it in a comment below. Listening to amateur bands can be a confusing experience. Sometimes there's good reception conditions, but nothing on the air. Sometimes it's opposite, and sometimes you get blasted with a CW contest in perfect conditions. I can't really tell if this is much better or worse than an RTL SDR in terms of reception, but that in itself is pretty cool, and I'm sure there's someone out there that can find a use case for a 200 kHz bandwidth direct conversion receiver. But what about frequency range? In the last video, I didn't manage to listen to FM broadcast radio because of the limited bandwidth that made any channel I tried listening to just alias and mirror onto itself. Today I think we'll have more luck, and since I already have the filter ready, we can just give it a try. Notice that I can't be bothered to change the LO frequency in GQRX. Obviously, we're not listening to FM broadcasts at 7 MHz. The antenna is still the same 40-meter wire in my attic, so it's not exactly tuned for the FM band, but of course the signals are powerful enough to make it past the mixer with just the right filter, even though they're not as strong as what's coming through around 7 MHz. Let's try changing the modulation to wideband FM and see what we get. That's pretty decent reception, but I better change the station before I get a copyright strike for playing Sabrina Carpenter. I've set all the channels to tune 50 kHz above center, so we're not affected so much by the DC center spike. But maybe I should have set them a bit further away. The coolest thing about this is that the SI5351 tunes reliably to frequencies around 100 MHz and handles the 90-degree offset into the mixer. Mixing down 100 MHz to baseband directly is quite a bit better than I expected. Going up to 144.8 MHz, as you see here, doesn't work so well though. But I can't tell if it's because the synthesizer can't keep up, or because it's close to double the PLL frequency of the STM32 F103 at 72 MHz. It's also a bit strange that some channels seem to have super good mirror rejection while others are only 10 dB away or even less. If you're interested, I have a few of these PhaseLatch Minis for sale, and I also have a few left of the PhaseLoom IQ mixers from the last video available. I also have PCBs available for both if you'd like to assemble them yourself, or you already have a Blue Pill style board. I've designed it so you can mount the filter and use a separate dev board. The PhaseLatch Mini really is just a sidetrack to my journey towards a decent modern software-defined radio with a 6502 at the heart of it, but it is a pretty cool dev board on its own, and it certainly deserved the build. If you're interested, most of the things I mentioned in the video are linked for sale in the description, along with the source code and design files for everything. I could say a lot more about the PhaseLatch Mini and all the hoops I had to jump through to make it work, but if you're really interested, I suggest you come ask me about it over on my Hackerspace Clubhouse Discord server. For now, I'll leave you with a few reception samples, and at the end you might see a spoiler about what we'll be taking a look at in the next video. Either way, thanks for watching.
hun lagde sig ind over kølerhjelmen på en bil. De har aldrig samlet så mange penge ind før. Altså, er du sindssygt, det virkede? Ja. Det må være alle mændene, der har siddet og kigget med.
Ja.
Det var godt
det virker.
Tænkt, ja.
Det virker simpelthen.
Ja.
Men apropos det der med...
Die russischen Stationen, die werden natürlich hier mit zunehmender Dunkelheit, sind die brutal laut hier und manchmal hilft nur eins abschalten. Aber nur gut, wir werden sehen. Wir können ja immer noch die Zeit vorverlegen, wenn sich dann das ungünstig herausstellen sollte. Ich bin dann weg. Deal 5 KCT, moin. So motiviert.